Okay. Hello, everyone. Thanks for joining us. My name is Nuruddin Sadawi. I'm from Imperial College London, and what I'd like to do today is I'm going to show you another aspect or another edge of phenomena. So what we're going to do today together is show how to implement a highly parallel containerized tools for large-scale data analysis in the phenomenal project. The title says metabolomics data analysis, but what we're going to see today is something that's generic, so it can be anything really that you can do in your code, anything they can do in your using a Docker container, then you should be able to run it on Phenomenal, as we're going to see. So straight to the talk. Phenomenal, as you must have learned by now, is an infrastructure that allows users to run common analyses and workflows on local or commercial cloud platforms. So we support Google Cloud, Amazon, Microsoft Azure, and as well as some private clouds like OpenStack, and you can also install Phenomenal on your local servers if you want. The main and primary interface of Phenomenal is the Galaxy platform, where you can create and run and share pipelines. We've seen that previously. However, we always wanted to have a place for those who enjoy programming, so the Phenomenal team have decided to take those on board, those of us who enjoy doing things programmatically to get interesting results, to get towards running novel experiments and so on and so forth. And that was done by including Jupyter, which is a Python project that allows you to run Python or R code. And because our main focus in this talk is on how to run parallelized tools, then let's have a look, or let's have a quick overview of concurrency versus parallelism, because these two concepts or these two terms can be sometimes used interchangeably, or in some books or resources you can find confusing definitions. So concurrency or multi-threading is in general is when two or more tasks can start, run, and complete in overlapping time periods. So this means they do not necessarily run at exactly the same time. Okay, and an example of this, of concurrency or multi-threading, is when we have, for example, a single machine, a single core, and then we do multi-threading or multitasking if you've done this in Java or C++ or some other languages. Okay, whereas parallelism is when two or more tasks are effectively and actually and literally running at the same time. Okay, so maybe on a multi-core processor where each core is running one task or one process. And to use Oracle's multi-threaded programming guide, concurrency there is defined as a condition that exists when at least two threads are making progress, and a more generalized form of parallelism that can include time slicing as a form of virtual parallelism. So you can see concurrency is virtual parallelism. So maybe it's a special case of parallelism where things run in a time slicing simultaneously. So they are effectively running at exactly the same time. And this is what we're going to do. We're going to run containers, multiple containers, and run them at exactly the same time. Okay. Now, in biology, to be specific, and in general, in many problems in computer science or biology or several other fields, so many problems are embarrassingly parallel. What we mean by embarrassingly parallel is that these problems can be divided into smaller sub-problems, and these sub-problems can be solved in parallel, i.e. at the same time or simultaneously, and then we can combine the results. So in order to process things in parallel, we need processing elements. By a processing element, I mean a core or a CPU or even a machine or a node in a network. So something that can process data. And you see, if you see this diagram at the bottom here, by having several processing elements, each one of them can have input, does the processing, and then gives us back output. And when we run them at the same time, we can in the end combine the results, and we will have saved a great deal of time. And when we run things in parallel, it's always good to measure or evaluate scaling performance. And in parallelism in general, we have two, or scalability in general, we have two paradigms. We have what is known as strong scaling and weak scaling. In strong scaling, what we do is we fix the data size. So imagine you have maybe thousands of data sets or thousands of samples or thousands of maybe images that you want to process. And what you do is you process these images or these data sets or these samples using a varying number of parallel processes. If I go back to the previous slide, you can process your 1,000 or 10,000 elements, data sets, for example, using one processing element, so you do them sequentially, or you can use two processing elements, you do them 2 at a time, or 5, you do them 5 at a time, or 10, 100, 1,000, depends on the resources that you have. So you fix the data and you change the number of parallel processes. And after you finish that, you can check the performance. We will see how to extract useful metrics in the next slide. Whereas in weak scaling, what we do is we vary the data size with the number of parallel processes, or the other way around. We vary the number of parallel processes with the data size, and in the same ratio. So maybe we can use 10 processing elements to process 10 datasets, or 50 processing elements to process 50 datasets, or 100 to process 100, and so on and so forth. And then we check the performance. So when we say check the performance, we mean we extract useful metrics, and that's what we see in front of us on this slide, that we can evaluate strong scaling using what is known as speed up. So speed up, as you can see, is T1 divided by Tn. T1 is the time taken to process the data. So remember, the data now is fixed, the data size is fixed. So T1 is the time taken to process the data using one processing element, whereas Tn is the time taken to process the same data using n processing elements. And then strong scaling efficiency is we basically divide the speed up by the number of processing elements n. So speed up is T1 divided by n times Tn. Whereas in weak scaling, because remember, in weak scaling, we vary the number of processing elements with the data size. So again, weak scaling efficiency is T1 divided by Tn, but it's a little different here. So T1 is the time taken to process 1 unit of data using one processor, whereas Tn is the time taken to process n units of data, so identical units of the ones that were processed using in T1, n units of data using n processors, okay, or n processing elements. And by doing that, we can divide T1 by Tn and then get weak scaling efficiency. Ideally, perfectly, we want to have strong scaling efficiency or weak scaling efficiency to be 1. That means we are making efficient resource usage, but that's not always true because of network overhead, maybe network communication between nodes and machines, or that's if we have a cluster, or sometimes when we transfer the data from storage to process and then write it back to the storage. So that takes some time, and therefore what we aim for is to try and push the weak scaling efficiency and strong scaling efficiency towards 1 as much as possible. So the higher, the better. The closer to 1, the better. Now, for the demo that we're going to have today, we will have a few assumptions. The first one is that Phenomenal is already up and running, so it's deployed successfully and it's running. And you have access to Phenomenal Jupyter and Luigi. Remember, currently these are password protected, so you have the password. You are already able to access them. If this is not the case, then please refer to other sessions where my other colleagues showed you how to install Phenomenal and how to configure things and how to access these services. And also, I'm going to assume that you have some familiarity. You don't have to be an expert, but at least you have some knowledge of Docker, Kubernetes, Python, and Luigi. And also, you're comfortable with using a terminal or the command line. Okay, so you don't have to be an expert, but at least you have some knowledge of that. Now, we mentioned that Phenomenal. The main interface of Phenomenal is Galaxy, but what we want to use here is we're going to use Jupyter and Luigi. So Luigi is a Python package for constructing elaborate workflows that consist of one or more tasks, and it's an interesting tool to use. That's why it was included in Phenomenal. When workflows are run, their status can be monitored using a web interface that comes with Luigi. So Luigi comes with the interface where you can see things running in a tree-like or a graph-like visualization. So when a workflow is run, it's handled by a Luigi worker. And then this Luigi worker is going to run inside a Kubernetes pod. So our colleagues in Uppsala, Sweden, they developed a Python module that's an interface between Kubernetes and Luigi. So that interface allows you to run Luigi workers inside Kubernetes pods, and that's exactly what we're going to use. So this module enables us to set up the resources using specifications that can be used by the Luigi worker, i.e. by the Kubernetes pod, and then we can run them in parallel. So we can run several identical workers in parallel. Bear with me, please be patient. If this is confusing, hopefully it will all make sense when we run the actual experiments. So in order to run the experiments we wanted to run, we have a toy problem. So in this toy problem, we're going to have 1,000 data sets, and we're going to do strong scaling. So we're going to run them using varying number of processing elements, or varying number of Luigi workers, as we explained in the previous slide. And the tool we have is a tool that is given a data set. It does linear regression, so performs linear regression, computes some metric, and then writes back that metric to an output file. And this tool is Dockerized, so it's inside the Docker container. I will show you the Docker file to create the Docker container, and it's run in this way: Docker run -v. So we do volume mapping. This data folder is on the host machine, and this /work folder is on the Docker container, and this is the container name, and that's an input data set. So what we do here is we pass it the data set, it does the processing, and then it writes back the output that it generates to a file that has exactly the same file name as the input file, but it just adds .out to it. Okay, and the reason we use volume mapping is so that we can keep the data. If we write the data into the container, and then when the container exits, we lose the data. That's why we use volume, so we can write the data to our volume, and then we can access it later. So the container writes the output to this .out file, same file name but .out. We have 1,000 data sets, and then instead of doing them sequentially, we will do them in parallel. And in order to do that, again, we're going to use Luigi. Now, how we're going to do that is I will provide you Python code that helps you create Luigi tasks, and then we will see that Luigi is going to communicate with the phenomenal cluster to download the Docker container from Docker Hub and then run it. So remember, this container now is saved online. It's on Docker Hub, okay, under my own account. And we will run multiple copies of this container. And just for your reference, you can see this link here. That's where I have everything for this demo. So you can access that link in your own time and then run these experiments at your own speed. So let's go ahead immediately to the deployment. Now here I'm accessing Jupyter on Phenomenal. I have a Phenomenal deployment up and running. Remember, this is password protected, so later on you can experiment with this, or if you have your own deployment, then you have your own password. And what I've done is I have basically done new terminal. So this gives us a terminal, and I created this linreg folder. This folder comes for testing purposes. I've created this linreg folder. So if I go inside it, this directory, what I have here is I have a Python notebook and then data.zip. So this data is the 1,000 data sets that we're going to actually process. And you might have a question that how can I actually access my data? Or how can I actually upload my data? There's more than one way of doing that. If you see here, you can actually upload the file, or if you zip your data, then you can upload it, or you can use the wget command if you're familiar with this command, or this Python notebook I have here is a notebook, or is some Python code that helps you download a file from Google Drive. Okay, so you can save your data in a Google Drive, maybe a zip file, compressed file, and then get the file ID and then run this code. That's where you provide the file ID, and then it will download it for you in that path that you specify. Okay, you can find this this Python code on my GitHub account. I'll show you that in a minute. Okay, but in the terminal now, I'm going to extract the data. Data sits in there. Yep, ready. So if I count them, and you can see we have 1,000 data sets. So clear the screen. And now I'm going to take you to my GitHub account. So that's my GitHub account. And if you click on repositories, you can see this is the code that helps you download a large file from Google Drive. Feel free to access it later. But this is the code or this is the repository that contains everything we need for the demo today. So let's go inside in there and have a look. This is the Docker file I use to create my Docker container. Feel free to have a look at it later. Okay, and we just basically pass it this linear regression to Py file, and then we run that file when we pass it the data set. And this is the linear regression file. And this is exactly what I meant by you can run anything. So this script runs linear regression, but you can have anything you want really. Okay, so you can do machine learning, some form of data processing, data analysis, anything you want. This is how flexible Phenomenal is. But the file that we are very much interested in now is this linreg file. This is the file that contains the specifications which we are going to use to run the container and run multiple copies of the container in parallel. So let me download this file to the notebook, and then I'll show you and I'll explain the contents in detail. So I've downloaded the file. If I go here, sorry, I need to move it to the linreg folder. I'm sorry. There you go, it's there. So the contents of this file or this Python script are very important. In the beginning, we import Luigi, and then we import this Kubernetes job task module that we mentioned before, developed by the Phenomenal team as an interface between Luigi and Kubernetes. And then we create a class. I name it linreg task, which extends that module or that class. This is where we specify the resources that are going to be used by our container. So what we do here is we tell this class that we need an input file for this when an instance of this class is run. So we need an input file, which is one data set. We give it a name. Feel free to name it whatever you want. And this maximum retrials here is just in case when if a pod fails, how many times do we allow Kubernetes to retry again? Hopefully it won't fail for you, but just in case it fails, how many times you can set, for example, to 3 if you wish. Okay, save, Control S. And then in this spec schema, this is where we specify the resources that our container is going to use. So here in this container part, we specify which container we're going to use. So here I say my Docker Hub ID / linreg. That's what my container is named. Doing it this way, this will tell Kubernetes to download that container, pull it down, and then run it. And then we pass an argument to the container. Remember, we said in the slides that we pass it a data set. So that's the data set name. That's how we do it. And here we specify the amount of resources that pod or that container is going to take when it's run on the Kubernetes cluster using Luigi. So we request 1 GB and 1 CPU, and we say do not exceed that. So limits 1 GB and 1 CPU. Okay, so exactly 1 CPU and 1 GB per container. Now, this is quite important to be aware of, this volume mounts configuration or specification. If you remember, let me take you back quickly to the slides. That here we mentioned we wanted to use Docker volume, so we write data to a volume so we don't lose the data when the container exits. That's exactly what we're doing here. We're saying volume mounts, the mount path is inside the container, so the container assumes that it will have a /work directory where the dataset is going to lie and where it's going to write the output file. The name is shared volume, don't change that. And then this subpath is on the host, so where we run this script. Remember, notice I have this linreg here, which is exactly the same name as the folder I mentioned before, or this directory I mentioned before, linreg. Okay. And then this volumes here is for Kubernetes setting by Phenomenal team, so don't change this. Okay. And now this output function is a function that tells Luigi when the task has finished, because what Luigi does is it keeps looking for this output file that we tell it to have here, and when the file is created, then it exits. Okay, so notice it's the exact same data file name dot out. This is how I configured it. Okay, this is something we explained here, that it writes the output to the same file name but dot out, right? And then this task here, or this class here, what it does is it only loops through all the CSV files in this folder. Okay, it loops through them using this glob method or module, glob module or glob Python package. It loops through them and creates a linreg task for each one of them. Notice we pass it the input file, which is here. So for each one of them, create one. So you might say, well, if you do that, then because we have 1,000 files, it will automatically get 1,000 tasks. No, this is what we do now using the code. So let's copy this little command to configure the Python path. This is to tell Luigi where to find the Python module, and then we copy this long command. Notice I have the time command to compute the time it takes to run this, and then I'll break it down to you a bit by bit. So time Luigi, this will we run using Luigi, and then the module name is linreg, which is this file here, this Python script, but notice without the .py extension. And then we run linreg all data sets, which is this. So this is the starting point of the script, and this will loop through all the data sets and then create a linreg task for each one of them. Okay, and this scheduler host is the scheduler host that's configured under Phenomenal to host Luigi. Okay, so this minus scheduler host tells Luigi where to submit these tasks that we're going to run. Remember, this linreg all data sets is the starting point of the linreg module we explained a few moments ago, and that way they will all be submitted to Phenomenal's Luigi service. And as I mentioned before when I was explaining the script, when we loop through all the tasks and create a linreg task, when we loop through all the data sets and create a linreg task for each one of them, that means the 1,000 will be done at the same time, right? But no, what we do here, if you notice the command, we say minus workers 100. Sorry, the screen doesn't fit properly here, but if we see it on the script, the screen there doesn't fit properly. So here, this minus workers here, 100, tells Luigi to do them 100 tasks at a time. And this is the parallelism that we spoke about throughout this talk, that here we can specify the number of parallel processes we want Luigi to run, and they will be run for us until all the data sets, or all, if you have any samples or images or anything that you can break down into smaller chunks, all of them will be processed, and Luigi will tell us or help us keep track of the status of those tasks. So let me press enter here, okay, for the task to start. And again, we mentioned Luigi, so I want to access Luigi. So admin and then your password. Remember this is password protected. Then here we see, save the password if you wish. We see how you have 1,001 tasks, because 1,000 tasks for each data set, and then the linreg all data sets task that combines all of them. And you can see here the pending tasks are 940 and running 61. If I refresh the page, then it's now exactly 100 are running and slightly more than 800 are running. I'm sorry, 100 are running and 806 are pending. What I can do here is I can click on this, on the main task name, so the starting task, and then if I do go to actions, view graph, then I can keep track of my tasks visually or graphically. As you can see here, these are the 1,000 tasks, one for each data set. The yellow ones are pending, the blue ones are running now, and the green ones are done. So yellow ones pending, running, and done. If anyone failed, then it will be red. Okay, so we just refresh the page, You can see all is running. And as you can see here, it's all still running. And okay, in the meanwhile, let me go back to the slides. Because what I've done is I have actually run or processed these 1,000 data sets using one worker only. So basically sequentially one task at a time, 5 workers, 10 workers, 20, 30, and so on and so forth. And as you can see, as we increase the number of workers, we do actually save a significant amount of time. So our parallel experiments are achieving what we wanted. So we are actually saving time, and we are exploiting the resources that we have. And again, the beauty of Phenomenal is that it allows us to do that programmatically, and it's so flexible that we can run really anything we wish. Okay, go back here to check still running. So refresh Luigi. We should see more green tasks now. Yep, so more of them, more and more are done. Again, refresh Luigi. Get more and more green. And then we will notice when Luigi knows that all are done, you will see the output here changes a bit. So so just making sure that everything has run successfully, and then finalizing everything. Okay, so this is what I meant, that you see Luigi telling you that okay, tasks are being finalized, so all of them are done. Yep. Yeah, as you can see, the 1,000 tasks using 100 tasks at a time took about 3 minutes and 15 seconds. So if you want to do more experiments, maybe you can change the number of workers to maybe 200 or maybe 50, according to the resources that you have, and you can basically compute the time. Like I said, this is what I've done here. As you can see the plot here, using different numbers of workers. But remember, one thing here is that because Luigi looks for the output file to be created to know that the task is finished, then remember to remove those .out files and then rerun the experiment again. Otherwise, Luigi will immediately notice that the task is already done because the output file is already there. Okay, so that's our experiments for today. And to summarize, Phenomenal does allow you to run tools via a GUI interface as well as programmatically, and that's one of the beautiful aspects of it. It means that it's possible to run really anything we want, any Dockerized tool that we have on this infrastructure, and scaling results are approximately linear. So if we now change the number of workers, then we can get better results. So if we double the number of workers, we hope to half the runtime, and if we half the number of workers, then the runtime will basically double. So it's nearly linear, and the speed up gain is significant. At the end of my talk, I'd like to thank you very much for your attention. I'd like to acknowledge and thank my colleagues from the different institutions involved in Phenomenal. And if you have any questions, please feel free to drop them in the text or contact us on Slack, or also feel free to email us. Thank you again for your attention.